Okay, so let us start with what we know about NP-hard problems. Okay, so I hope everybody here knows what NP hardness is and how do we show NP hardness. Like how do we give an evidence that a problem is not polynomial time solvable. So how do we do it? Anyone? Like all of you know this, right? So what is it? What would be your approach to show that a problem does not has a polynomial time algorithm? You can be loud. Okay, so basically you start from a problem A and you have problem B. So which one is harder? A is say known to be say NP hard, okay, and this we do not know. This is our problem at hand, and you reduce. And what do you mean by reducing?
In polynomial time, you convert a general instance of A to some specific instance of B.
Okay, if you are given an instance I here, you convert to an instance I prime here, such that I is a yes instance of A if and only if I prime is a yes instance of B. And so this conversion should be polynomial time, right? Okay, does anybody know any other way to prove that a problem is NP hard?
You show that any general problem in NP can be reduced to B.
But this is what you're doing here.
You're taking NP hard problem. You're already saying that I already know of an NP hard problem.
Yes.
But suppose you don't know of any NP hard problem.
Okay.
So how will you prove that a problem is?
No, suppose you know many NP hard. No, now you know, right? Why are you assuming? Like we know so many NP hard problems. So how do you know any other way to show NP hardness? No? Okay. So let me give you another method and let's see what happens. Okay. So I will call it method. So here what we do is, so look, what is the goal of doing this reduction? Essentially what we are doing here is, if you give me an algorithm for B that runs in polynomial time, then I will design an algorithm for A that runs in polynomial time. This is what we are doing by this reduction, right? So now let us look at a new method which is an algorithm. This will be an algorithm for problem A. Okay, so there is some subroutine, say sub as the subroutine is, but say you guarantee that this is a polynomial time subroutine. Okay, now what I do is it may call this subroutine for B multiple times. This is subroutine for B. Okay, this is algorithm for A. Okay, and take some input. So this algorithm can call this sub-alg many times. It's not necessary that it calls just once. It can call multiple times and say it does some processing on that outputs. So it makes some call, it gets an answer. It does some more processing, it again calls the subroutine, gets another answer. So the answers can be dependent also. Okay. So now if I manage to design such an algorithm and say I have for simplicity say I call t instances. So I1, I2, I up to say IT. Whatever input this was given. Okay. Now I made t instances of this problem B. And now I compute some, this can be dependent also, they need not be independent. So I may create instance I2 depending on what was the output of instance I1. Okay. So it may be dependent also, it may not be completely independent. And now there is some function, this by this subroutine sub-alg So here we have this sum function of sub alg b of I1 comma sub alg b of b of IT. Okay. So this is what this algorithm is doing, and I tell you that if you can solve this correctly, if you give me a correct subroutine which runs in polynomial time, then I can do this fancy method and give you the answer and solve. Then what are we doing? We are solving this problem A in polynomial time. So if you are giving a polynomial time algorithm for problem B, I am solving this problem A in polynomial time, which will rule out that come on, this we assume to be NP hard, so it's very unlikely that your algorithm is correct. Okay? Okay. So why have you not seen this fancy method? Is there any reason why most textbooks that you read just gives this definition? Because this seems much more powerful, no? This is allowed to create dependent instances, and this can be any function, right? It's just expected that this function is computable in polynomial time and you can generate these instances in polynomial time. You are even allowed to create instances depending on answers of the previous instance. So then why is this definition not there? Because this captures the essence of this NP hardness much more than this. Yes, it proves. But yes, because look, if you had such an algorithm, alg A, then you are showing that if you design this sub alg B, then this becomes polynomial time solvable, right? Yes, we start with our working hypothesis is so A is NP hard. So this is our working hypothesis.
Sorry, so you're ruling out that B is polynomial time.
Yes.
But that does not prove NP hard, right?
So but look, what are you doing here? Why is it not NP hard? Like, so okay, let's talk in terms of whether a problem has polynomial time solvable algorithm or not. Let's fix this definition, okay? So suppose we just want to say that problem B does not has a polynomial time algorithm, right? So are these two methods equivalent or this is more powerful? Just think about it. Okay, so I leave it as an exercise that why textbooks don't give this definition and they are good with this definition. And we will see this in the context of parameterized complexity also. Okay? So look, it is just an algorithm. It creates multiple instances. It does some processing, I don't know what, but it has some computable function f, okay, does some processing and outputs me the answer. If you guarantee me that you can design this sub alg B for problem B that runs in polynomial time, I guarantee you that I will also give you a polynomial time algorithm for the problem A. This we do here also. This is the same approach, right? But now here you are just creating one instance, right? So, but here you are allowed to do so much more. You can create multiple instances, you can create new instances depending on the answers of the previous instance. And you can, it's not yes instance versus yes instance. You can have any function. Look, this is a Boolean function and this answer is also Boolean. We are in the decision version of the problems, right? So, either the answer is 0 or 1. So then there is some reason why we don't get to see this as part of the definition, right? Because look, the thing that you are saying that problem is not NP hard, that does not hold here because look, if you can design such an algorithm, then you're actually, what is NP hard problem? So if you can solve this problem, I can solve every other NP hard problem, that's it. That's what NP hardness means. So in particular, if I even design this type of algorithm, right? So I will show that this is essentially a different kind of reduction from A to B, right?
No, actually, it's not. Like, for example, if you can even solve three certain polynomial time, but you won't be able to solve a halting problem if, even if you, because it's undecidable, but it's
No,
just
but
NP-hard.
who said that halting problem is NP hard? Like, look. The point is, but you can solve every other problem which is reducible to it, right? So here, why do we not see something like this? So actually, try to show that these two things are more or less equivalent. They are actually, okay? I'll keep this, and this, why I wanted to introduce this method is the best way to see reductions is an algorithm, because reduction is nothing but a fancy algorithm which uses algorithm for another problem as a subroutine to solve your problem. So in my opinion, this is a very important perspective for reductions which we don't get to see. Okay. So by this I'll start by, we'll see and try to think why these things are different, and if you don't get an answer we can discuss this later. But just think why these two things are not equivalent, if they are not equivalent, and if they are equivalent, why is this definition never given and this is given. Of course, if you show that they are equivalent, then this is simpler to state, right? Okay, so think about it, this is an exercise, okay, and let me know if you don't succeed, then we can discuss it. Let's go back to parameterized complexity. So in this talk we will see that certain problems may not admit an FPT algorithm, and we will see how we can give an evidence that this problem does not admit an FPT algorithm. So this is captured by what is called W hardness. So we will take more like algorithm designer's perspective than a complexity theoretic perspective, and we'll see, we'll just be interested in giving evidences that okay, this is not FPT. Okay. So for that we'll see, so first before giving further details, it is worth noting that the when we say that a problem is unlikely to be FPT, it is under certain complexity theoretic assumption. Why is it under certain complexity theoretic assumption? Because look, we do not know, take a problem which is unlikely to admit an FPT algorithm, which will be Clique for us. We do not even know whether Clique is polynomial time solvable or not. We do not know whether P equals to NP or not. We are in the in the assumption that P not equal to NP, but maybe somebody disproves it, then these things will collapse. So our assumption, so when we say that a problem may not have an FPT algorithm, must also be conditional. It cannot be unconditional, right? Because a polynomial time algorithm is also an FPT algorithm. This is why it is necessary that we must have a conditional theory here also, because we do not know whether or not P equals to NP. So our polynomial versus non-polynomial solvable problems are also based on assumptions. Okay. So let us see what parameterized reductions are. So I hope everybody is aware that a parameterized problem is a mapping from sigma star cross n to n. So this is our a problem Q. We can represent any parameterized problem like this because we have the string, we have the parameter, and we have some map. Okay. So now we have, actually we can say, that, so this is, since we deal with decision version of the problem, this can be treated as 0, 1, and thus we can treat a parameterized problem as a subset of sigma star cross n, right? Because this takes all the yes instance of this language, all the no instance are outside this. So now let us look at two parameterized problem. So parameterized problems. Okay, and what we say is a parameterized reduction from A to B is an algorithm that given an instance x comma k of A outputs another instance x prime comma k prime of B such that first x comma k is a yes instance of A if and only if x prime comma k prime is a yes instance of B. The second condition is that the parameter k prime should be bounded by some g of k. The third condition is algorithm say calligraphic A. So A must run in time some f of k into size of x power some constant c. C is a constant. Okay. So this is what we mean by parameterized reduction. So essentially what does this say? So if you have two parameterized problems, here you have A, here you have B. So given an instance x comma k here and here you create an instance x prime k prime via this algorithm calligraphic A, what do you get? So now here you spend time some f of k into size of x power some constant. This much time you can go here. Now if this problem has an FPT algorithm, so say this problem has some h of k type of FPT algorithm, by k I will always denote the parameter, okay. So here suppose you have something like this, then what you can do? You can go, we can design an FPT algorithm for the problem A as follows. You apply this reduction, you spend this much time. Now notice that k prime is bounded by some g of k. Okay. So now how much time will you, suppose this has algorithm of running time something like this thing C prime, then how much time you will additionally spend is h of g of k, because k prime, this k will be this k prime, right, which is g of k into how much can be size of x prime? Exactly this much, right, because in this much amount of time you can just write this much amount of information. So this is the size bound on x prime, right. So now this x, this size of x, this is something like f of k into size of x power c into c prime. So then notice that this you can show that it is an FPT algorithm. Okay, why is this function an FPT algorithm? Why you can bound it by f of k alone? Because here you are using a property. No, look, yes, and look, here this was supposed to be k, okay, which is k prime. Here I will write, to avoid confusion I will write it like this. So here notice that, suppose let me give the function h, okay. So h looks like, I am just specifying some values. Of course it is a mapping from n to n, but I will just specify some value. So it looks like, say 1, 2, 3 up to 4, 5 and so on. Here it is 100, 2, 100, 50, 19, 10, 2, 1, 1. Suppose this function is a decreasing function, then can you still say that it's okay for you? Because look, although you have preserved the parameter, you are spending more time. So had it been h of k, look, the parameter was k, but here you are applying with g of k. G of k is larger than g of, so if look at this thing, g of k, if you look at this thing, Okay, so basically if k, look at k1 and k2, if k1 is less than k2, this function h has f of k1 is greater than f of k2, right? Can you still apply this? Right? So we need the property that these functions are increasing. They are not, if not increasing, they are at least non-decreasing. Okay? So then, but this assumption does not hurt us, because suppose a problem has an FPT algorithm which has a decreasing function, you can easily convert it to a non-decreasing function by taking max over all k's which are from 0 to that particular k. That's it. So if the problem, if your problem has an FPT algorithm which has a decreasing function, then it also has an FPT algorithm with respect to some non-decreasing function, right? So because take the max, right? That's it. So this is, but this we use, with this property is crucial to show this functions. Okay. So let us remove this and let us go back to our different method. So what? Because the gist with which I was introducing all this was whether a problem has an FPT or algorithm or it does not has an FPT algorithm, right? But now this is one method. Let us go back to our previous method. We can do the same thing. Suppose you give me a subroutine, this sub alg b. So here we have A and B. An FPT algorithm for this problem B with respect to some parameter, and I create some instances, say many, which is still FPT many instances, and I can compute this because F we are using here. So let us call this. If I can compute this function in FPT time, you will still be able to obtain an FPT algorithm, right? Because what we were saying, so if you give me if you give an FPT algorithm for problem B, I will give you an FPT algorithm for problem A as well, right? So I might as well apply this, right? Who is stopping me, right? So actually, although you did not realize, even in the NP hardness case, you have seen such reductions. You may have seen such reductions, I assume, which is called Turing reductions, where you do not create one instance but multiple instances. But why is it still okay? Right? So this you have to think, and here also just think about why do we go to this simpler definition and why do we not complicate our lives by stating those things. Okay, because stating this thing formally is more difficult. It's not very difficult, of course, it's just a definition, but this definition is much more parsable than this definition. So there has to be a reason why do we stick to this definition, although that looks much more general, right? Because you are able to do much more things there, but still you want to stick with this definition. So there has to be some reason, but once you figure out the case for this polynomial time solvable problems, I'm sure you will figure out why we use this definition here also. Okay? Right. So this was the definition, and let's see one important property of this parameterized reduction, which is transitivity. So what it means is, so let us see. So in this, transitivity will be important for us. Okay, I'll say what this transitivity is. So if then there is a reduction from into C as well. Okay, so does anybody see a proof of this? course not people who have seen it multiple times, but for others. So why should this statement be true? Do you have any idea how to prove it? What would be that? Yeah. Exactly. So basically, you have two algorithms. So you have algorithm say A1 here and algorithm A2 here. Given an instance x comma k here, you can convert it to an instance x prime k prime here, and this you can further convert to some x double prime k double prime here. Notice that here k prime is bounded by some g of k. Here k double prime is bounded by some g prime of k prime. So you compose these two functions and still you can obtain that this k double prime is bounded by some function of k, right? Okay. Now this is a yes, so here you have yes instance equivalence, here you have a yes instance equivalence. So because this relation this is if and only if condition, you can obtain that x comma k is a yes instance if and only if this is also a yes instance. Okay. Now running time. So how much time you spend some f1 k into size of the instance power some c1, here you spend time some h of x prime k prime x power c2. Now if you compose these two things, you will obtain that indeed it's an FPGA algorithm. So these parameterized reductions are transitive. So why is this useful for us? Why do we want to have a transitive property, or why do we want to highlight that there is a transitivity property? Okay. This I think everybody can remember. So I will erase this. So notice that when we are proving something to be NP hard, we start from some problem and we reduce it to some other problem in the usual definition, right? Now, when you're designing any reduction, often it turns out that starting from some problem may be easier than starting from some other problem, right? So this is where transitivity helps. So suppose you were able you were able to conclude that B does not have some algorithm based on the assumption that A does not have such an algorithm. Then you have two choices of problem. Now you can, when you are trying to say next, given evidence that the next problem does not has an FPT algorithm, you can either start from A or you can start from B, right? So if you either manage such a reduction or manage such a reduction, in either case you can say that if A does not have such an algorithm, C also cannot have such an algorithm. Here also by transitivity you can say that if A does not have algorithm of certain type, then C also does not has algorithm of a certain type, right? So and it may be very useful to start from problem B instead of starting from problem A. So this is why this transitivity is quite helpful for us. So now let us see why. So suppose you have two problems A and B, and you manage to give a parameterized reduction from A to B. Okay. So suppose A is NP hard. Can you conclude something about B? Can you say that B is also NP hard?
This polynomial is also f, I mean, just a function of k, and in parameters we need more time.
So is this also problem NP hard? So your answer is yes or no? How many people say that it is yes? No voting? No raising hand? So how many think it is, this can be, we can conclude that B is NP hard? At least one. Okay, so let's see. So this is actually not true. Look, here what is the time allowed? Exactly, right? So here you are allowing FPT time, and if you cannot conclude from here that B does not has a polynomial time algorithm, right? Because for I am asking whether or not it has a polynomial time algorithm. So you cannot conclude this. And actually this was just a philosophical note, but we will see a concrete example where this should not be true. Okay. So I hope everybody knows the Clique problem. We are given a graph G and an integer K. I will just write it. So let's look at two versions of Clique. So first is Clique and Clique log. So here the input is graph G, integer K, and the question is, does there exist X subset of Vg, cardinality of X equals to K, such that here intentionally I am writing equals to K, okay. This in the standard definition it is greater than equal to K, but you can always work with equal to K also, that's not an issue, such that graph induced on X is a Clique. So here the input is actually the same with an additional condition. Here the input is graph G on n vertices and an integer K, where K is at most say log n. Okay, is the input clear? And the question is again, is there X subset of Vg, size of X equals to K, such that graph induced on X is. So what kind of algorithm can you have for this problem? The trivial algorithm, any trivial algorithm would do. It may not be polynomial also. Exactly, right? But what is the running time bound now? Exactly. So here the time you can easily obtain an algorithm, admits an algorithm with running time n to the order log n, right? Here you have such an algorithm. Just a note that for NP-hard problems you do not expect such algorithms. So we do not know whether it is in NP or in P, or so it is NP-hard or not at this point, of course under assumptions, but we do not expect such an algorithm for a problem which is NP-hard. So this problem most likely is not NP-hard. But we do not know, we will not speak about any polynomial time algorithm for this problem at this point, okay. Now let us go back to our Clique, okay. So and let us try to give a parameterized reduction from here to here, okay. So the goal is to give a parameterized reduction from Clique to Clique log. So here we want a parameterized reduction, okay. Any guesses? No. We do not expect a polynomial time algorithm for this problem. That's what I'm saying. When any problem admits an algorithm of running time, something like this, we do not expect that that problem will be NP-hard.
You mean whenever there might be an inherent parameter?
No, this here I am not talking, here there is no parameter, right, at this point when we are designing into the, so this problem, look at the problem Clique log, okay. This problem most likely does not admit a polynomial time algorithm. This is what I am saying, okay. So if any problem, because how to convert a parameterized problem to non-parameterized version, just forget the parameter and keep everything the same, right. So here, so this problem we do not expect any polynomial time algorithm because it admits an algorithm of such type, and for some reasons if any problem has algorithm of such type, we do not we believe that it will not be polynomial time solved, okay. Let us give a reduction from Clique to Clique log. So any suggestions? It's not very difficult. Exactly. Right. Yeah, just say. So we are given given an instance g comma k. What we do is, so we can create. So suppose this is our graph g. What do we do is, we keep this graph g. It is on n vertices. Say cardinality of vg is n. What do we do is, we add, say, 2 to the k isolated vertices. Just give me a minute, okay? N can be log. Yes. So here want is k is at most log n, right? So you can here take order log n also. Let's take it order log n. So here notice that what is k? K is the same. We are looking for clique of size k here also, but the number of vertices is n plus 2k, and we are looking at a clique of for a clique of size k. So k is actually, so this we do not need order actually. So k is at most log of n plus 2 to the k, right? This property holds. So therefore we gave a parameterized reduction in time 2 to the k into poly n, which converted an instance of clique to clique log. So this was a parameterized reduction, right? So suppose you denote this graph by g prime and you have the same parameter k. So notice that g comma k is a yes instance if and only if g prime comma k is a yes instance of clique log. Because look at a clique here, okay? This clique is also present here, right? So here the same clique will work here, and if you look at the reverse direction, if you have a clique here, notice that it cannot pick any of these additional vertices because they are isolated vertices. We of course we can safely assume k is greater than equal to 2, right? Because one vertex is trivially solvable. So now the clique must be contained here, which is of size k, but then that clique is also a clique of size k here because the graphs are the same. This is an induced subgraph of this graph, right? So we actually showed a parameterized reduction taking the problem clique to clique log in parameterized time. This is NP hard, but this we do not expect to be NP hard. So this the type of conclusions I was asking, is not valid. So we cannot conclude that the other problem is also NP hard. Okay? So please stop me and ask questions if there is any confusion, okay? So for some time we will take clique as one of the hard problems. By hard what I mean is it does not admit FPT algorithm. So for some time we will assume that clique is our paradigmatic paradigmatic problem which does not has an FPT algorithm. Okay? So we will so now we will look for problems parameterized complexity which are as hard as the clique problem. Not clique log. Now we are back to clique. We are given a graph, we are given an integer, and we want to test if there is a clique of size k or not. Okay? Here k has no additional condition. It's just some number. Okay. So now what we'll see is, so as you may have some experience with proving NP hardness, it turns out that if you have more structure on the input, that can be exploited in a better way. So if you have more structured form of input, it's easier to design reductions starting from these kind of problems. So as a simple example, let us start from clique and let us show that clique on regular graphs is NP hard. So let us call it regular clique. Okay, so what is regular clique? The input is again a graph G and an integer k, but here the degree of each vertex is the same. That is what a regular graph is. Okay, So a regular graph is if you pick any two vertices, the degree of both these vertices are the same. So this is what we mean by regular clique. Okay. So now we'll show that regular clique is actually as hard as clique. So regular clique seems to have much more structure, right? It has, every vertex has the same degree, but it turns out that it is of no use, not that much of use, and we'll show this by giving a reduction from clique to regular clique. Okay. So here we are given an instance g comma k, and we would want to create an instance g prime comma, we'll decide some k prime such that g comma k is a yes instance of clique if and only if g prime comma k prime is a yes instance of regular clique, and we want that g prime is a regular graph, is an R regular graph for some R. We don't know what that R is. So before that, suppose I give you a 3 regular graph. Can you do something? So if the input graph itself is 3 regular, can you solve this problem? What? Exactly. So that admits polynomial time algorithm. So here the R that we will get cannot be a constant. It has to be something larger than a constant. Okay. Let's start from clique. So we have this graph G. So what do we do is, so let D be the maximum degree. Max over degree of V in G, V belongs to Vg. Okay, D is this number. So we would want to make the degree of every other vertex same as D. Okay, so for this what do we do is we create D copies of this graph G. Okay, so we have, so I will denote them by G1, G2, G3. So we have created D copies. Okay. So now what we want to do is we want to add some more things so that we can make the degree the same. So now for each vertex V here, so notice that V has a copy V1, V2, V3 to VD here because it is joint copies. Okay. What we will do is we will create a set of vertices denoted by V subscripted by this small v. Okay. The number of vertices that we create here will be something like D minus degree of V in G. So if D already has degree D, we do not create any other vertex. Okay. If it is if its degree is small, then only we create these vertices. Okay. Right. Now what do we do is, so look at, we create a, we add all possible edges between these copies of the vertex V. Yeah. So we look at any vertex V here, look at its degree. Say its degree is D1. Okay. So I create D minus D1 many vertices. So these are D minus D1 many vertices. Okay. So for every vertex based on its degree. Right. So in particular, if you look at the vertex which achieves the maximum degree, for that I do not create any vertex. Okay. Right. So now what do we do is we add an edge between this, we make, so for every this Vi here and for every vertex here we add an edge between them. So if you look at copies of this vertices V1, V2 up to Vd and newly added vertices say U1, U2 up to UL, they have all possible edges between them. Okay, is this construction clear? So we have, we do this thing. So notice that what is the degree of this vertex? Exactly D, right? Because it is adjacent to exactly D many vertices. Okay, good. Now, this, what is the degree of a vertex here? D. because it has been made, whatever the deficiency was there, we covered here. That is why each vertex here has degree d. Okay, good. So now this graph is a deregular graph. Okay, so we can assume that this k is at least 3 or something, right? Because if it is at most 3, we can solve it in polynomial time. Okay, okay. So now let us see that if the original graph has a clique of size k, if and only if this modified graph, let us denote it by g prime, has a clique of size k. Okay, so look at the forward direction. Forward direction is very easy because if you have a clique here, this same clique is present in all copies, right? So pick a clique, the same clique from any of the copies, and you get a clique of size k, right? So you're done. So now let us look at the reverse direction. Okay, so notice that a clique cannot have vertices from two different copies because there is no edge between them. Okay, so the clique is either here or here, right? Okay, so now just a minute. Okay, so now we have assumed that we have some clique has size some 3 at least. Okay, so if notice that no two vertices of this type can be selected, because if you look across this V, okay, even across these vertices, they together form an independent set. So no two vertex can be selected, at most one can be selected. Okay, so you can select at most one of them. But if you select one from here, then you can select only its particular copy. So the vertex corresponding to which it was created. So if you selected say U1, which was in VV, then you can only select this vertex V here, right? Because only it has no edge to anybody else, and you are looking for a clique. So actually, when you are looking for a clique which has size at least 3, it has to be a subset of here, right? And that's it. So once you get that the clique has to be contained in one copy and does not contain any newly added vertices, this clique is also a clique here. That's it. So basically what did you do? So you were given this instance, you converted it to an instance here, and you proved the equivalence. The parameter was the same, so this did not do. There is no adjacency. Yeah, this is why we can argue that a clique cannot pick vertices from both places. Okay, right. So yeah, so this property is satisfied. This property is satisfied because we said k and k prime are exactly the same. They are equal, and it runs in actually polynomial time, right? Because what is degree? Degree is at most n, right? And you are creating at most n copies. So this is a polynomial time procedure. So in particular, it is also bounded by this. And that's it. This is why you can show that regular clique is as hard as the usual clique. So let us do something more interesting. So let's define so everybody will remember this, right? I hope it's not very difficult. So I can rub this, and so do you remember what perfect hash families were? Does anybody remember? You remember, right? Saket had taught. Okay. Let's do something non-trivial and interesting. So let us define problem. Pi graph. Don't know what to call. If you have a better name, then please tell me. Let's pi interesting. Okay. So what does this problem restrict to graph problems? Okay. So here in G some integer k, and the question is x has size k such that satisfies pi. Pi is some property. Pi is some interesting property, or any other property that you find interesting, and we just want that if you look at x, then it satisfies this property pi. This is our pi interesting problem. Okay. Now let us define another problem. So colorful pi interesting problem, or multicolored, just to be consistent with the literature. Interesting problem. Okay. So now here what we do is, so input is integer k, and you have partitions v1, v2 up to vk, a partition of vg. There exists x subset of vg, size of x is exactly k, such that first satisfies this pi. If you look at for every I, x intersection vi has size exactly 1. Okay. So suppose I tell you that this problem is does not admit an FPT algorithm. We'll see how you can actually conclude that this also does not admit an FPT algorithm. So though you know how your solution should look like, you just are allowed to pick one vertex from each part, you still would be able to conclude that if the interesting problem that which you started, if that does not has an FPT algorithm, so does then this can also not have an FPT algorithm. Is there any confusion? Are you not able to see anything? Okay, if my writing is bad, please let me know. Okay. So let's see how we can do this thing. Okay. So some of you may already know this for at least one problem, which is our famous, two problems actually, which is the famous multicolored clique problem, multicolored independent set problem. Of course the reduction there is much more simpler, but actually we can say this for much general problems. Okay. So can someone recall me what a perfect hash family is? Anybody remember? Anybody who remembers? So Saket would have defined this. So you are given, what is the input first you have to tell me, right? So given an integer n comma k, okay. So we'll say assume n is less than equal to k for simplicity. Sorry. Okay, k is at most n. What you so a family of functions which look like f, which is a map from 1 to n to 1 to k. One to k. It's called nk perfect hash family, right? Yes, it's n comma k perfect hash family if for any s subset of 1 to n where size of s is k and any function g from s to k, okay, So actually you don't need this fancy definition, you can actually say that this is enough for our purpose. I'll just write what is enough for our purpose, okay. So for any given S which is subset of n of size k, there exists some function f in this family such that if you look at f restricted to this set S, then this is an injective function. So it is fine, so it's also bijective, so it does not matter. So is the definition clear? Everybody remembers the definition, right? Okay. So what it is saying, given any set S, if you look at this function will assign elements of S. Okay. So they will all be distinct. This is what this is saying. So given any such set, okay, you will always have a function which maps it injectively. This is what perfect NK perfect hash family does. Okay. So and you may have seen this result that what is it?
Definition, like the other form was like when you're given any other G
Yeah.
that respects the G. So by injective here, what if the colors like I mean
We are not talking about colors. There is nothing. This is a separate result. This is a separate problem and this is yeah.
I'm just telling here take like 1 to k is color.
Yeah.
1 to k. It's a function. I'm just telling you coloring.
Yes.
So here what I'm asking is here what the previous definition was for all G, for all functions which map S to K, there exists something which respects this. That was the thing. But here what you're telling by injective, you're just pointing out one type, right?
Yes, but this will be enough for our purpose. What I'm saying. So given any set, there will be a function which maps it injectively. That's it.
There is a function, but the previous definition was for any function. So even if you have all the permutations, there exists something.
Yes, but this will be enough for our purpose. We don't need.
No, I'm asking. Are
Yeah.
you saying that these two are equivalent definitions, or you're just telling for the purpose of reduction?
Uh, I don't remember, but I think the definition was this. We can check the book, but the point was that F splits this set evenly. That was the definition, right? What was the notion of evenly? Evenly means if you take size same, then it has to be injective, as far as I remember. Yeah.
I think Sakita did 20%.
Oh, okay.
Whatever you are defining, just define that and stick with it.
Okay, okay. Okay. It's not this the universal set that he defined yesterday. That's different. This is perfect hash family. Oh, he told me that he defined. Okay, well, never mind. Okay, so this is what perfect hash family is. Okay. Okay. So what there is a theorem which says that the family a perfect hash family for given for any n comma k where k is at most n, we can compute a perfect an n comma k perfect hash family of size e power k power order log k into log n in time e power k power order log k log n into n. Okay. So what this theorem says is, in FPT time, if the parameter is k, then in FPT time you can compute a perfect NK perfect, you can compute an NK perfect hash families of this size in this much time. Okay. Note that the time is FPT, so size should also be FPT. Okay. So this is what the theorem says. Okay. Let us go back to our this special thing. Okay. And let us look at a different kind of reduction, and we will see that using this we can do something more. So I wrote this first so that while I am describing the reduction, you can figure it out that you can do the reduction usual way. Okay, this is why I wrote it. So given this your interesting problem that you chose, let's do the following. So we are given an instance g comma k of pi interesting problem. Okay, what I do is I randomly color the vertices using k colors. So I assign color I with probability. So I random with 1 by k probability I'll assign this color. Okay, so this way I get partition into k sets. Okay, so we are going from here to here. Okay, okay. Now let's see, and I return this as my instance. So integer, the graph is the same. This is my partition, and I put the same integer, and I ask the question. Okay, let us see what is the probability that you can guarantee that this is also a good instance for you. Okay. By good instance I mean, look, forward direction, so what you have to show? In general we show that I comma k is a yes instance if and only if the created instance is a yes instance. Here we'll say that with good probability you achieve this. Okay. So notice that one direction always holds. Suppose you find a solution here, because it is a subgraph, the graphs are exactly the same, the x will satisfy the property pi here also, because it satisfied some additional properties, but it satisfied what it had to satisfy. So if you give a solution here, I'll always be able to give you the correct answer here also, right? So the problematic is going from here to here. So given a solution to this solution for this instance, how can I show that there still will be a solution for this? We cannot do it directly because maybe all the vertices in X are present in V1 for some reason. Then we are not able to return it. So suppose there is a unique solution, and somehow our coloring was not good and we ended up coloring all vertices of X and we put everything in V1, then it's a problem because there was a unique solution, right? So we cannot say it exactly, but we can say that with good probability we are good enough. So what is that good probability? Let's see. So what do we want? Fix a solution in your head which is of size k. What do we want? That this solution should be colored properly. By being colored properly, what I mean is no two vertices of this vertex from the solution should get the same color. So what is the number of colorings that you have for n vertices? So what is that probability? The probability of good event. What is the total number of possible colorings? This one? Okay. So what is the probability that your solution is colored the way you want it to be colored? What did you say? K power? This one? Into? Because what you want? You just want the first vertex should get color 1, second vertex should get, so if the vertices of X look like say x1, x2 up to xk, you want x1 to get color 1, x2 to get color 2, xk to get color k, but they can also get permuted, you don't care, right? This is why there is a k factorial, and this you have this, that's why. So this can be bounded by how much? You have seen this. This much. So then so basically if you repeat this process FPT many times, you will succeed with constant probability, right? So this is a simple randomized reduction. Okay, let's de-randomize this reduction. Okay, why do we have to go via this randomization when we have something very special here, right? Okay, so now you knew the definition, you had an idea of what we wanted to do, so can anybody say what we should do? So you know how our randomized reduction work. You have this definition. Can you do something interesting?
According to every function, it is family of function according to every function, color it and return the cardinality of many instances at many instances.
Okay. Okay. So basically given one instance, so what she is saying is given one instance g comma k, we do not create one instance, but we create multiple instances. Okay. So in particular, for every, so first we start by computing this perfect hash family. Because we know what n is, we know what k is. So we start by computing our nk perfect hash family. So we have this family f computed. This we can do in FPT time, right? Once we have computed this, for every f in f, we create an instance which is denoted by, we create a graph gf. So gf is same as g. We have integer k and we have this partition pf which is given by the countings. Right? So this function, look at this function, right? So this, each of this function, it's a map from 1 to n to 1 to k, right? So here look at these functions. What are these functions? These functions are of this type, right? So you can you can label the vertices of the graph as 1 to n. You have n vertices, you can label them from 1 to n, okay? So now look at this, so we are considering a fixed function f. So f is a function from n to k, okay? So now pick 1 in V1. So this is f inverse of 1 is V1, okay? So put in V2 you put f inverse of 2. Okay. Look at all those vertices which are colored 2, okay? And so on up to Vk. So this is f inverse of k, okay? So this is what you do. So for every such function you create this instance. Now we want to show that g comma k is a yes instance of your interesting problem if and only if one of these instances is a yes instance of your multicolored pi interesting problem, okay? So again the reverse direction is trivial because the graph is the same. You give me a solution here which is colored, I can forget about the color and obtain a solution. So the point is we have to obtain the forward direction, right? Okay, so how do we obtain the forward direction? We have this G, have been given a solution x here which has size k, okay? So now what do we do? Yes, so now check for this x, check which is that function, because there are just this many functions. You can test which is a valid function for you. By the property of this function there exists one which will put it in different sets, right? But now this is a yes instance, then x is the vertices of x are distributed like this, and now you can show that the x is also a solution here, right? Notice that if you had an FPT algorithm for this problem, then you can actually solve this also in FPT time, right? Okay. So notice that here we did not create one instance but multiple instances, right? And this you should think, you please think why this is like, why this fits the notion of our definitions, okay? Why is it still okay? It's a not very difficult exercise but a nice exercise to think, and please let me know if you don't figure out the answers, okay? So this is how, if you have, you can show something like this. So usually it turns out that problems like multicolored clique, multicolored independences are very useful for proving W hardness. So if you see many of the W hardness results, W1 hardness results, then they start from multicolored version rather than the usual clique and independent set versions. So the colored version sometimes can give you much more structure, and it can be useful. So this can be a useful property to have. Okay, so now this was not in book, but I thought that it's an interesting thing to know. But now let we see some W hardness results from the book. So, and I hope that this gives you some algorithmic flavor of the thing that I was talking in the beginning. That you may have an algorithm that does some stuff, it creates multiple instances, though of course you are not deciding here what instance to create based on the answers of the previous things, but it creates multiple instances. It is actually a Turing reduction, not the usual Karp reduction. Okay, so let us look at our dominating set problem. Do we have T2? I have no idea. You have to go to the top floor. It's not 3:30 yet. I cannot leave you before 3:30. Sorry. Or I won't leave you before 3:30. Integer k and the k says that we have, there exists x in x such that v belongs to set problems. Okay, so what in more human words, so we want to find a subset of k vertices such that either the vertex is in the solution or one of its neighbor is in the solution. This is what dominating set problem is. Okay, so we will see that the dominating set problem is not easy, not an easy problem, and it is as hard as clique and multicolored clique and whatnot. Okay, so let's see how we go about it. So uh, by the prototype problem, that this pi interesting, we can also obtain that multicolored variant of clique does not has an FPT algorithm, right? So there is a simpler proof for showing multicolored clique does not is W1 hard, which is a polynomial time reduction actually, but by our prototype we also obtain that. Okay. So now let us see, suppose we are given, so we will give our, so what click and go to okay. Okay, let's see how this reduction works. Okay. Okay, so basically what we have to do is, firstly we have to encode that what is the instance here. We have k parts here. The first thing that we want to encode is that one vertex should be selected from each part. Okay, this is the first thing that we need to encode. This property is then we have additional property that it should be a clique, but let's try to encode the first property. Okay, so suppose we have we keep also we have this parts like this which look like v1 v2 up to vn. So we can assume that by adding dummy vertices we can assume that each of the parts have n vertices. Okay, so v11 v12 v1n v21 v22 v2n V31, V32 up to V3n, VK1, VK2, VKn. Okay. So what do we do is we make here a clique. Okay. But notice that, is that enough? So by creating a clique, we have many edges. In some sense, we have some structure that, okay, we may have to pick a vertex from here to dominate this, but it is not enough. Okay. So we will do little more thing here. What we will do is we will create, let's see what all things we do and what turns out to be enough. Okay. So suppose I add here one additional vertex, say x, okay, and make it adjacent to everybody here, and this is a clique. Okay. For we'll see why this making this clique is useful, because then if we pick anybody from here, all these vertices will be dominated. So this is why we want to make it a clique, so that in one go we dominate everybody here. Okay. So now, but notice that everybody may be dominated from outside also. So how do we ensure that we pick something from this part? So to do that, let us add one vertex which is adjacent to everybody. Now this vertex needs to be dominated. Okay, but then it can be dominated by itself also, right? So then why, so to ensure that we don't choose this vertex, let's add another vertex y1 which is not dominated by x. So it is also adjacent to everybody else, but they two are not adjacent. Okay, so notice that x and y cannot dominate each other. So if I have to dominate something, it is better for me to pick something from here, because if x and y will have no other roles, more or less. Okay, so they can only be dominated from here. These vertices will not play any role in future also. So their only goal is to say that, okay, somebody from here should be selected, because I need to be dominated. So x1 says that I should be dominated, y1 says that I should also be dominated, but they cannot dominate each other. So in a sense, a smaller size solution should prefer these vertices which are originally in the set V1. Okay, so this is why we add this, and we have these two vertices which are non-adjacent, which are adjacent to everybody else. Okay, so this will ensure that one vertex from every part must be selected, because xi and yi from which are added to part I cannot be will not be dominated from anywhere else. In my rest of the construction, I will make sure that they cannot be dominated from anywhere. So they will have no other neighbors. So from each part, I must select at least one vertex. Okay. So so our picture has changed a little. So we have this. So we have here x1, y1, x2, y2, x3, y3 up to xk, yk. Okay, and we have our original vertices here. So now what we have achieved is, we have achieved selection of one vertices from each part. Okay, so the property 1 should be satisfied even with our current set of edges that we have added. Okay, so we do not, this is not the graph G. Okay, so the graph G is here, which has part 1, V2, V3 up to Vn. Okay, these edges are not here. What I have done till now is I have just encoded that from every part one vertex must be selected. Okay, okay. So now, but I also want that this is not enough for me, right? I want that the vertices that I select must form a clique, right? So what do we do? Notice that if we, so this is a clique here, so this looks like this, clique. So we have edges here. So we have something like this. Okay. So now I need to ensure that it forms a clique. So for this I have to somehow encode these edges, because these are the edges. These edges tell me who can be part and who cannot be part, right? So I need some way to encode the edges. Okay, so let us fix an edge here which is between say u and v. Okay, consider the edge E equals to uv. Okay, so vertex u is here, say vertex v is here. So what I want is, so if u and v both are selected, then there must be an edge between them, right? Because we want a clique, right? Here what do we want? We are in the in the multicolored clique. What we have k parts, and we are looking for a clique which contains one vertices from each part and induces a clique. So k vertices, we have encoded selection of k vertices, but now we want them to form a clique also. Okay, so what we have encoded till this point is that we must select one vertex from each part. What we have not encoded is why they should form a clique. Okay, so now suppose I select u vertex u from here and vertex v from here. I need that there has to be an edge between them in the original graph. Okay, but then directly adding this edge is useless, right? What is the point of adding this edge? So we have to do something more to encode this. Okay, so for that what we do is we add a new vertex, say EUV. So for every edge we do that. So let me use a different letter. Let us say this is WE, where E is this edge UV. Okay, now what I want is I will make this vertex VE adjacent to everybody else apart from U, and here I will make it adjacent to everybody else apart from V. Just a minute. Okay, right, so that's it. This is the construction. Okay, and let's see why this is enough to encode all our edges and encode that the clique property is also satisfied. Okay, let us look at forward direction. So in the forward direction, just give me a minute. Pick this one. Okay, so let us look at okay, so this is how we encode edges. So let's look at the forward direction. So suppose G has, we are in the forward is not this, so we have G K V. Okay, and graph induced on X is a clique. Okay, so now what we do is okay, so suppose this is an we do it, so for look at every non-edge, for every non-edge we do this. Okay, so every non-edge which is present here we do this property, this thing. Okay, so now let us look at forward direction. So we have this clique, and let us pick exactly the same vertices here. Pick X here also. This is our graph G prime. Okay, so now notice that all these vertices are dominated xi yi, because I select one vertex from each part. All the vertices that are present here are dominated. Now we have to worry about this vertices that we have added, this vertices corresponding to the non-edges. Okay, so look at a non-edge here. So non-edges, look at a pair UV. If there is an edge, it is an edge. If there is no edge, then it's a non-edge. Okay, that's it. Okay, so now let us look at two vertices. So let us look at any WE. bar. Okay. So because we have dominated all vertices, we need to dominate the vertices corresponding to the non-edges. Okay. So we have some this thing which looks like UV is some UV. Okay. So say it is between part V1 and Vi and Vj. It does not matter. So U is here, V is here, and it is connected to everything here and connected to everything apart from V here. Notice that since UV is a non-edge, right, both U and V cannot be in my solution because I want a clique, right. So this means that I have selected either somebody from here or someone from here. We know that we have selected one vertex from here and one vertex from here. So suppose that those vertices are U and V from these parts, then note that it's a non-edge, right, and we are starting with X which forms a clique in G, right. X is a clique in G, but U and V do not have edges in G, right. This is why this vertex VE bar is there in the first place. We have added vertices corresponding to non-edges only, right. So then this cannot happen, okay. So this is why there cannot be, so every vertex, every such vertex is also dominated, okay. So this completes the forward direction. That if you have a solution here, you can find a dominating set here of size k. Let us look at the reverse direction. Okay, so the reverse direction is, we know that one vertex from each part must be selected. Okay, because notice that we have budget just k. So this graph is G prime and k. We want that from each part we have to select one vertex. We cannot select xi or yi because then who will dominate the other one? If I select xi, x1, who will dominate y1? Right, because this cannot be dominated from elsewhere, it has to be dominated here. So a vertex from Vi must be selected for, because Xi and Yi are there, okay. So we have selected k vertices. Now let's see why they form a clique, okay. So why they form a clique? So suppose look at U, if they do not form a clique, then there is UV, U in part say Vi and V in part some Vj, which have a non-edge. But if they have a non-edge, I have a vertex W E bar, where E bar is this pair UV, right? But now notice that this vertex can only be dominated by vertices here or here because it has no adjacency at other parts. But its neighbors are everybody else apart from U and everybody else here apart from V. And I have only selected U and V from these parts. So who is set here? That's it. So it must be, so when you have a dominating set here, you can lift it to being a clique in the original graph. Okay. So this this shows that the dominating set problem is as hard as the multicolor clique. Okay.